Dear students, we have seen three techniques for rank aggregation so far. We started with the Bodas method, which is a classical method which dates back to 1871 and was primarily used for social choice theory, but later adopted for rank aggregation on the World Wide Web. Then we also looked into the Shimura technique of fuzzy ordering, which is again a classical technique, but the same had been used for rank aggregation on the World Wide Web. And then the last one that we saw on the previous turn or the lecture was the Dubois and Parade method. In fact, the very idea with Dubois and Parade was that if considering the mean position of documents alone is as good or as bad as the Bodas method, then maybe if we rope in the variance also, the variance of position of documents in the various lists, then it should improve because variance brings more information than the mean alone. So with that hope, we had gone to Dubois and Parade method. But Dubois and Parade method unfortunately turned out to be a brute force method and also gave bad results. So that sends us thinking, where have we gone wrong and what improvement should we do? So in that sense, we have gone to another technique which is called membership function ordering. So the amplitude of the membership function of each document at each position is evaluated using the expression for the expression that we have seen, this expression, right? Gaussian membership. So we are using this very membership, but it is just that beyond this point, we are not going to continue with the Dubois and Parade method. Rather, we will do something else. So the document having the highest membership value at a given position is assigned to that position. This way the documents are arranged in the aggregated ranking. So we have taken the Gaussian membership function for each document based on their mean and variance and the Gaussian membership expression. And after that we can see at position 1, which has got the highest membership value or degree of belongingness, because membership value is degree of belongingness. So whichever has got the highest degree of belongingness at position 1 should be stuck to position 1. Then we come to position 2. So over here, this one is having the higher membership function. And at this point, again, this is having the highest membership function. But since this has already been given a value before, so that is why the next highest should be considered, right? So that way we can go on doing what is called membership function ordering. So we find out the mean position of documents across the lists. We find out the variance of the position of documents across all the given lists for all the documents. And then we try to find out the membership value of all the documents across all positions. You remember? Uh, see, uh, in the Dubois and Parade method, we have done this already. Document 1 has membership value at position 1. It has membership value 1.5 into 10 to the power minus 3 at position 2, 0.31 at position 3, 0.664 at position 4. And for document 2 also we had got it. At position 1 it is 0.231, at position 2 it is 0.48, at 3.231 and 4 at 0.025. But in order to apply membership function ordering, we will have to find out such distribution of membership across positions for all the documents. So in this slide, we will see that we have got it for all the documents, all the participating documents across the 4 positions. So first of all, we look at position 1. At position 1, we find that D4 has got the maximum value. So that means D4 fits position 1 the best because it has got the maximum degree of belongingness at position 1 in amongst all the documents, right? So our aggregated list should have D4. After that, we come to position 2. Now position 2, again D4 has got the highest value, but since D4 has already been given position 1, so it should go out of contention. So amongst the remaining one, let us see. Amongst the remaining ones, we see that D3. D3 has got the highest value. So D3 is taken care of. Okay. So D4 is taken care of, D3. Now coming to position 3, we see that amongst these two, D4 has got the highest value. Sorry, D2 has got the highest value. You see here this one, D2. And this was the basis for D3. So D1 also goes out of contention, and what is remaining, which in fact has the maximum value also at position 4, will be D1. So our aggregated list, see, so maximum value at first position amongst all the documents, that goes to document 4. So for the rank aggregated list, aggregated rank L, L of the first position will go to 4th document. This is what it means. So you see that we get 4213. Let me see, have I gone wrong somewhere? Oh, yes. I have gone wrong. Actually, this was the highest value at position 2. So it should not be D3, it should be D2. My mistake, right? So in the third place, there'll be a contention between D1 and D3. So they are having a tie actually. So D1 and D3 are having a tie. So what I can do, I'll put a D, and instead of this, I'll place an equal sign, right? So I'm sorry, I'd gone wrong. So ultimately it should be 4 to 4 to 3. 4 2 3 1 or 4 to 1 3, because 3 and 1 are tied up for the third and fourth position. So the tie is being resolved arbitrarily. So this is how we can carry out the membership function. So again, steps are: find out the mean position of all the documents across the list, find out the variance of all the documents across all the given lists which are participating in rank aggregation, and then find out the membership value at each position of all the documents using the Gaussian membership function, which is already given. Then start from position 1. Which of the documents has got the highest membership value or degree of belongingness? You take it there. Right? So after the first position is fixed, we go to second position, and then we see of the remaining documents, leaving alone what has been fixed at position 1. Of the remaining documents, we try to identify the document which has got the highest membership value at position 2. So we pick it up likewise at position 3, likewise at position 4, 5, 6, and so on. So this is the technique of membership function ordering. But again, this membership function ordering at least talks about Gaussian membership value, right? And Gaussian membership expression requires the exponential function evaluation, which may take a little longer. So we are looking for an additional, another method which may be simpler and utilizes the mean and variance advantage, mean and variance coupling advantage, putting them together, the advantage of putting them together. It tries to exploit. So we will see that. Before that, let me tell you a point of concept. You see the membership expression that we have talked about, Gaussian membership function that we have seen, this one. Actually, this is a probability distribution function, right? So area under the curve would be 1. So if you have got a function which is having a lesser spread, it will have a higher peak. And the one which has got a higher spread will have a lesser peak, so that the area under the curve remain 1. So such kind of membership functions are called subnormal membership functions, because their peak may not necessarily be 1. You see, peak is varying, their peak is varying. So I'm giving you a general concept that if you take such a membership function which doesn't have peak 1 at any point, such a membership function in the domain of fuzzy logic is called a subnormal membership function. Why have we used subnormal membership function here? And why not a normal membership function? That we will see when we talk about the next technique, which is mean by variance technique. It may be noted that if the variance of the position of two documents is same, then the document having a lesser mean position must be ranked first. We all know about membership, Gaussian membership. You see, the peak occurs at the mean position. We all know that. And this spread is based on the variance. Higher the variance, more the spread. Right? And lesser the variance, lesser the spread. Right? So I'm just making use of that. If suppose I'm taking a membership, two documents which are having membership functions in such a way that their variance is exactly the same, but their mean positions are different. So the one which has got lesser mean will occupy an earlier position because its mean will occur earlier. And the one which has got higher mean will occupy a later position in the ranked list. So that is about mean. Then coming to variance, the one which has got higher spread will have better occupability at earlier positions because its spread is more. So lesser the variance, more pointed it would be, or more belongingness it would have at its mean position. And higher the spread, it will have lesser belongingness at its mean position and higher belongingness earlier. So we see that mean and variance, we can take their ratio found for all the M documents. An ascending sort and the set of these functions would give the aggregated list L. See, lesser the mean, earlier it would be, and higher the variance, earlier it would be. So lesser mean, higher variance, right? So we take their ratio. So let us see how do we do it. Suppose we are given to aggregate three lists. We are finding out their mean position. We are finding out their variance, right? This is what we did in Dubois and Parade method also, in membership function ordering also. Now from here we depart. Instead of going to the Gaussian membership function to find out the degree of belongingness at each position, we just take their ratios, which is so easy. Just ratio. Division process has to be done as opposed to the exponentiation problem that would have been required whenever the Gaussian membership function was required, as in the Dubois and Parade method, as well as in membership function ordering. So that way mean by variance turns out to be an easier method, right? We just take their ratios. So MBV1, which means mean by of document coming out to 3.67 divided by 0.22, 3.67 divided by 0.22, this one. And this comes out to be 16.68. Likewise, MBV2, mean by variance of document 2. So this has to be 2 divided by 0.67, right? Comes out to be this. MBV3 is likewise x3 bar divided by sigma 3 square, 1.56. And then finally 1.67 divided by 16 point, divided by 7, where is it? Divided by 0.22, divided by 0.22 would give me MBV4. Now on sorting these in an ascending order, we get, just hold on. Should be sorting a descending order. Just hold on. Lower the mean, earlier the position, right? Lower the mean, earlier the position. And higher the variance, earlier the position. So yeah, ascending order. It should do ascending order. Mean by variance, ascending order. So we get 3, 2, 4, 1. Right? So Just hold on. Which has got higher mean by variance value will have earlier position, right? Higher mean by variance value, which is having higher mean by variance value, or lower mean by variance value, sorry, which has lower mean by variance value. Which one is that? MBV1 is 16.68, MBV2 is 2.985, 1.71, 7.5. Okay, so fine. 3 is coming first, and then 4 is coming, right? 3 is coming first, and then MBV4 is 7 point, MBV2 is 2.985. So MBV3 is having the least value, then 2.985, and then MBV4 comes next, MBV4 comes next, and MBV1 comes in the end because it is having the highest mean and least variance. Okay, so that is why it is coming out to be the last. So this will be our aggregated list using mean by variance technique. The last technique that we will consider before we compare all of them. So till now we have seen Boda's method, we have seen Shimura technique, we have seen Dubos and Parade, we have seen membership function ordering, we have seen mean by variance technique. Now we are going to improve the Shimura technique. How do we do that? We feel that the poor performance coming from the Shimura technique is primarily due to the employment of you remember we had this preference matrix, and then we used to find out the min function row wise to get a value here. In Shimura technique I'm talking. Then the min value across all the row elements to find out this value, then min value. Now the problem remains, whenever we find out the min value, only the min value is there and the spread of the remaining elements is simply lost. So what makes more sense? It makes more sense to use ordered weighted averaging. You remember ordered weighted averaging came in only because min is not a good function, right? So we have to employ ordered weighted averaging. So just in the last step, if we replace min function by ordered weighted averaging with a proper linguistic quantifier, my Shimura technique will get improved. Okay. So the min function results in many types, and not only ties, but also it loses the useful information amongst the remaining elements. Arbitrary result in deterioration of the aggregate. We therefore propose to replace this min function by an OWA operator. Now, obviously, OWA operator will perform better than the min function, but the question is which linguistic quantifier should we use? For that, we have a clue from what is called Condorcet criteria. It says if a page spams fewer than half the participating search engines, the spam page would occupy the bottom partition of that aggregated ranking which satisfies Condorcet criteria, right? So we get a clue from here. Do I have, just hold on a minute. So for the sake of completeness, I have added Condorcet criteria here. You can see that I paused the presentation and then I added this Condorcet criteria, right? So first let us understand what is Condorcet criteria. If there is some element which defeats every other element in pairwise simple majority voting, then this element should be ranked first. What does it mean? If suppose there is a document DI, right? Now, when I compare document DI with document D1 across all the lists, right? So if it is having more, if it is performing better in the majority of the lists, suppose there are 5 lists, 3 lists are such that DI is occurring ahead of D1. There are at least 3 lists in which DI is better than D2. there are at least 3 lists in which DI is better than D3 and so on, then this DI should be documents and this DI should be ranked. So for the sake of clarity, let me repeat it. Condorcet criteria. What does it mean? If there is some element which defeats every other element in pairwise simple majority voting, then this element should be ranked first. So by now you should be able to understand if there is a document DI which is better than D1 in the majority of the lists, it is better than D2 in the majority of the lists, so on. It is better than DI minus 1 in the majority of the lists. It is better than DI plus 1 in the majority of the lists, and it is better than DN in the majority of the given lists. Then DI should be ranked first. So this is Condorcet criteria, right? Now, use this Condorcet criteria and read this. If a page spams fewer than half the participating search engines, the spam page would occupy the bottom partition of that aggregated ranking, which satisfies Condorcet criteria. If we have any rank aggregation method which satisfies Condorcet criteria, then it will be ensured that if a page is spamming fewer than half the participating search engines, suppose there are 5 lists to be aggregated, and the spam page is able to influence just 2 of them, then such a page would definitely come in the lower half in the aggregated list L, right? Suppose I have L1 coming from search engine 1, L2 coming from search engine 2, L3 coming from search engine 4, 3, and 4, and L, right? Right. Now, if a page is able to influence or, spam only less than half of them, then this aggregated list will have that particular page in the bottom half. In the bottom half. It cannot come in the upper half. It would be the lower half, provided that it is able to spam fewer than half the participating search engines, right? So the whole picture is like this. If a page spams fewer than half the participating search engines, the spam page would occupy the bottom partition of that aggregated ranking which satisfies Condorcet criteria. So it will come in the lower half. Suppose there is a page. Suppose there is a page DJ. Okay, but DJ is able to influence only less than half of the participating lists. And is often from rank aggregation method which satisfies Condorcet criteria, then this DJ will occur in the lower half and it cannot come in the upper half. It cannot come in the upper half. Now, one question remains, what if DJ is able to spam more than half the participating search engines? For our example, suppose it is able to spam 3 or 4 or 5 lists more than half, then the simple answer is that in that case, we can't do much. That is a garbage in, garbage out situation. If you are giving more garbage, more than 50% garbage, how do you expect a good output at the end? Right? Got it? So this is the concept behind the improved Shimura technique, that for this reason, we have decided to use the relative fuzzy linguistic quantifier at least half with the pair. This at least half is coming from the this one, fewer than half the participating search engines, right? With the pair for the purpose of finding the vector Ci as follows. This part, ordered weighted averaging, this part, where Zi is the jth largest element in the ith row of the matrix, Fxi xj, where xi xj is obtained from Shimura technique. Let us take the example, things might be more clear. Example of improved Shimura technique, Fxi xj, we have found out this. Till this part we have done in the Shimura technique. From now on, in the Shimura technique, what we were doing, we were taking the min of this, we were taking the min of this, we were taking the min of this, we were taking the min of this. In the improved Shimura technique, instead of taking min, we will take at least half of these four values, at least half of these four values, at least half of the four values in a given row. For the number of criteria, I'm it is half with the pair A is equal to 0.0, B is equal to 0.5. The corresponding linguistic ordered weighted averaging would have the weighting vector. You can find out, you can check for yourself. It will be 0.5, 0.5, 0, 0. Now, 0.5 into the largest plus 0.5 into the second largest plus 0 into third largest plus 0 into fourth largest. So that will give me the first point, right? 0.5 into 1, the largest is 1. 0.5 into 5, second largest is 0.5, and this is my W2, this was W1. Then W3 is 0, and the third largest is also 0. W4 is 0, and fourth largest is also 0. So that comes out to be 0.75. This will be 0.75. Likewise, C2 will be 1, C3 will be 1, and C4 will be 1. Descending sort on Ci, I is equal to 1 to m, gives the aggregated rank. Again, in this case, we see there are a lot of ties simply because the values are too little. The matrix is too small. If you go to a realistic search engine, it may be a 100 by 100 matrix at least, if you are just considering the top 100 documents. If you consider more documents, this matrix will be even larger, right? So in that case, the chances of tie would be lesser. Okay. Now we did experimentation for all these techniques, and the experimentation procedure falls in line with the ones found in literature. We have taken the same 37 queries that people had been doing in the past. These were the 37 queries. We are also using the same 7 search engines: AltaVista, All the Web, Excite, Google, Hotbot, Lycos, and Northern Light. For each of these search engines, we are taking only the top 100 results, which means our matrix would be 100 by 100. Aggregating these results using our soft techniques that we have seen: Boda's method, Shimura technique, Dubois and Parade, then membership function ordering, mean by variance, and improved Shimura technique. Comparing the aggregated list with the ones obtained using Boda's method. So this is our result of rank aggregation. So Boda's method, aggregated distance we found out was 0.5132. By aggregated distance, I mean normalized aggregated Spearman foot rule distance, which we have discussed already. So it was coming out to be this, and time relative to Boda is obviously 1. Boda's method compared with Boda's method time will be 1. Shimura technique was quick, but its result deteriorated because we want to minimize the distance, right? Spearman foot rule distance has to be minimized. If you remember the very definition of rank aggregation we gave in the beginning. So it has to be minimized, right? But in this case, it has increased. When we went to Dubois and Parade, it took so long because it's a brute force method. It took so long as compared to Boda's method, and the result also deteriorated. Now, when we came to MFO, that it is here that the result has started improving, although in the third place, but it improved as compared to Boda, as compared to Shimura, as compared to DP, and it took lesser time also. MBV, time shouldn't be less because this is faster than MFO. And its result further improves in the third place of decimal than MFO. And improved Shimura is the best, right? In terms of time, it is pretty reasonable, better than even MFO and MBV, and of course better than DP. Not as good as Shimura in terms of time, but then its normalized aggregated Spearman foot rule distance has become less as compared to all these techniques. Now you might be wondering why I'm so praiseworthy about a change happening at the third or the fourth place of decimal, because these are all sparse lists, partial lists. You remember, these are all partial lists. The results coming from the actual search engines are partial lists. So had they been full lists, then this result would have been much better. This result would have been much better, right? So this is about the soft techniques for rank aggregation, starting from Boda's method to Shimura technique to Dubois and Parade, the membership function ordering, mean by variance, and improved Shimura. On the next one, we will see the genetic algorithm based rank aggregation technique. So that will give us not only a lesson on how to do and why to do genetic algorithm, but also what advantages it brings in and what improvements it brings in. So we will stop here and we will see genetic algorithm based rank aggregation on the next one. Thank you very much.